Today's lesson is Atomic Theorists, or the scientists who shaped the model of the atom. So, do theories in science stay the same? Of course not. Ideas and theories in science change as new information is gathered. So, our theory about the atom has changed over time as new studies are done. Even though no one has ever seen an atom up close, we are still able to make new discoveries, just like we have made new discoveries about dinosaurs. So, what do dinosaurs and atoms have in common? The fact that no one has seen an atom or a dinosaur directly. We know of their existence only by indirect evidence. So our theories of both have changed over time based on this indirect evidence. So what is an atom? An atom is the smallest particle that an element can be divided into and still be that element. For example, the smallest particle of carbon is a single atom of carbon. If you divide it, it is no longer carbon. So an element is the smallest piece of an element that is still that element that maintains that identity. So for the atomic theory, scientific knowledge builds on past research and experimentation, and the atomic theory has changed over time as new technologies have become available. So we're going to watch this brain pop real quick, and we'll be right back with the notes.
Ooh, a present. Dear Tim and Moby, how do we know what atoms look like if we can't see them? From Darren. Yeah, atoms are small, real small, too small to be seen in any detail. Still, scientists can do experiments that tell them things about what makes up an atom. Right you are, my robot pal. You can't see what's inside the box, but shaking it can give you clues as to what's inside. It's the same with atoms. Using indirect means, scientists have been able to construct different models of the atom. This atomic model has taken years and years to build, and people still tweak it now and again, hopefully making it more and more accurate. At the beginning of the 19th century, Englishman John Dalton built an atomic model called the atomic theory of matter. According to his theory, each type of matter is made of only one type of atom. Also, each type of atom could be put into a group called an element, and every atom of a given element was identical. For example, gold atoms make gold, iron atoms make iron, and so on. These atoms were way too small to see. Dalton also believed atoms could not be created, divided into smaller parts, or destroyed. So far, so good. About 100 years after Dalton, British scientist J.J. Thomson discovered the electron. Thomson used a vacuum tube with metal plates at both ends and an electrical source for his experiment. He found that a beam would form between the two plates, the cathode and the anode. Putting a magnet near the beam caused it to bend, which meant that the particles of the beam were electrically charged. Thomson discovered that the cathode rays were made of negatively charged particles, later called electrons. Because matter is mostly neutral, with no net charge, atoms must contain both positive and negative charges that cancel each other out. Thomson stated that negatively charged electrons must be stuck all throughout a positively charged area. Think of it like the atom is cookie dough and the electrons are chocolate chips. The discovery of electrons was a big deal, but it left some questions to be answered. Where were those positive particles holding those electrons in place? In 1909, a New Zealand-born British scientist named Ernest Rutherford and his team set out to answer some of these questions. They beamed positively charged alpha particles at a sheet of really thin gold foil. Because so many particles could pass right through the thin gold foil, Rutherford hypothesized that the gold atoms must be made of mostly empty space. But some of the particles did bounce off, so Rutherford revised his hypothesis to say that a gold atom must have some very small, positively charged mass. He named this mass the nucleus. He called the positively charged nucleus particles protons, and said that the electrons were scattered in empty space around the nucleus. James Chadwick, a student of Rutherford's, found new particles in the nucleus that weren't affected by an electric field at all. Alpha particles in the experiment had knocked them loose. Chadwick called these uncharged particles neutrons. Also in the early 20th century, a Danish physicist named Niels Bohr discovered that electrons are arranged in energy levels. The lower energy levels are closer to the nucleus and can hold just a few electrons. The higher energy levels are farther away and can hold more electrons. Since then, scientists have refined the so-called Bohr model. Electrons have levels, but they don't orbit the nucleus in neat little circles. Instead, they exist in a region called the electron cloud. The atomic model is constantly evolving as scientists discover more and more about what makes the universe tick. Oh, okay. Go ahead and open it. Hey, it's an atomic model. Well, you have to put it together. That's not right.
So the first atomic theorist we want to look at is Democritus. He is going to be around 400 BC. Democritus was a philosopher in ancient Greece. He began the search for a description of matter. He thought that matter could be divided into the smallest piece. Like he could just keep dividing it, it would get to a small piece that couldn't be cut any further. He questioned whether matter could be divided into smaller and smaller pieces forever until eventually the smallest possible piece would be obtained. He believed that the smallest possible piece of matter was indivisible, and he named the smallest piece of matter atomos, meaning not to be cut. So to Democritus, atoms were small, hard particles that were all made of the same material, but they were formed into different shapes and sizes. So that's how you got different stuff. So he kind of like a Lego model idea. Then we have Aristotle, who's not really an atomic theorist, but we have him because he is credited with the death of chemistry for nearly 2,000 years. So in ancient Greece, Aristotle declared that all matter was made of only four elements: fire, water, air, and earth. And he believed that matter had just those four properties: hot, cold, dry, and wet. Aristotle had a lot of influence over the public at this time, and his ideas were generally accepted for centuries. So the death of chemistry ends in about 1803 with John Dalton. He performed a lot of experiments and eventually he led the scientists to accept the idea of the atom. He formulated the first atomic theory since the death of chemistry, and he theorized that all matter was made of atoms. The atoms are too small to see. Now, he held on to that uncuttable idea like Democritus, thinking that they could not be destroyed, they could not be broken down into any smaller parts. He also theorized that all atoms of a given element are exactly alike and atoms of different elements are different, which is true. After Dalton, we have Thomson. In 1897, J.J. Thomson provided the first hint that an atom is made up of even smaller particles. So we're getting out of that idea of this itty bitty thing that can't be cut down into anything smaller. Um, he discovered the presence of a negative particle in the atom. We call that the electron. He proposed the model of the atom that sometimes is called the plum pudding model in Europe. Here we can kind of refer to it like a chocolate chip cookie model. His theory was that the atoms are made of positively charged substances with negatively charged electrons scattered about, like raisins in a pudding or chocolate chips in a cookie. Then we have Rutherford. So 1908, which really isn't that long ago, we have a guy from New Zealand named Ernest Rutherford. I'm going to tell you now, Star Test likes Rutherford for some reason. He comes up a lot, so really keep an eye on him. But he performed an experiment called the gold foil experiment using positively charged particles fired at gold foil. Through this experiment, he found out that atoms are not a pudding filled with a positively charged material. Instead, he theorized that the atoms have a small, dense, positively charged center called the nucleus. He said that the nucleus is tiny compared to the rest of the atom as a whole, and that because of that, the atom is mostly open space. So the volume of an atom is mostly empty space. That means we're mostly empty space because we're made of atoms. He concluded that the negatively charged particles are scattered outside the nucleus at a distance. Our next guy is Bohr. In 1913, the Danish scientist Niels Bohr proposed an improvement to the atomic model. So he came up with this model that we still use, and you'll have to learn how to draw and what the rules are for drawing these models. Even though we know it's not quite right, we still use it because it's a good visual. So the Bohr model has the electrons going around the nucleus, kind of like the planets orbit the sun. So they go in concentric circles around the nucleus, and the electrons are in different energy levels. So you'll hear that circle called a lot of things: orbital and energy level. Um, but just know that we're talking about the rings around the nucleus. In the Bohr model, the orbits or energy levels are located at certain distances from the nucleus. So even though we use the Bohr model, we now know, the theory most accepted now is the modern cloud theory, the theory of the electron cloud. According to today's atomic theory, electrons do not orbit the nucleus in neat planet-like orbits. The electrons move at high speeds around the nucleus in the electron cloud. So the electrons whirl around the nucleus billions of times in 1 second. They're not moving around in random patterns. So Bohr was right with the levels because they do have different amounts of energy depending on where they are in relation to the nucleus. So an electron's location within the cloud depends upon how much energy the electron has. So if you've studied atoms before, you know that there is a part missing that we did not discuss. So we've talked about protons and electrons. Well, the neutrons were actually discovered by a guy named James Chadwick, and he was a student of Rutherford. So if you want to write that down, I'll put it on the board and I'll put it out later. And just so you have that information, just in case it might be an extra credit question or something. But his name is James Chadwick, Chadwick. He discovered the neutron. So the next little video clip that you're going to see talks about the size of an atom. So it's pretty interesting, but that'll help you as we move through the unit.
13, IBM released the smallest movie ever made. It's a simple stop-motion short film, but what makes it special is that they controlled the placement of individual atoms to tell their story. Everyone knows that atoms are tiny. They're the building blocks of all matter, but I don't think people fully appreciate just how small atoms really are. You see, you can't just use a regular microscope to look at atoms. They're literally too small to interact with light, making them invisible. You have to use a special machine called a scanning tunneling microscope, which basically maps the electrical charges of atoms to create a model representation, like what the researchers at IBM did to make their movie. Even though it seems like we're looking at individual atoms, we're really not. So what does an atom actually look like? I mean, if we were to scale one up to the size of a tennis ball, it would probably look like this. Nothing, and that's because atoms are mostly empty space. Let's take a simple atom like hydrogen, for example. It consists of just an electron and a proton, but the electron doesn't simply just orbit around the proton the same way a planet orbits around a star. Instead, there's a field which shows where an electron might be found, and these fields are what define the size of an atom. The shape of these fields can get kind of weird when you start adding more electrons, but for hydrogen, it's simply a sphere. To really drive home just how empty atoms really are, if we were to instead scale a proton up to this size, the entire atom would be 8 kilometers wide. That means this hydrogen atom is the size of downtown Los Angeles with a tiny electron somewhere within this sphere. It might be 4 kilometers that way, or 4 kilometers this way, up there, down here, or anywhere in between. If you thought finding a needle in a haystack was impossible, try finding an electron in an atom. But let's go back to when our atom was the size of a tennis ball. And atoms come in various sizes, but for this video, I'm making the assumption that an atom is 1 angstrom wide, or 1/10 of a nanometer. Our tennis ball is 67 millimeters wide, making our scale 670 million to 1. A group of atoms like this is called a molecule, and this one in particular's name is adenine. And there's nothing special about these individually, they're fairly simple, but when formed together, they become something very cool. They become the source code of all life, DNA. Now, traditional models of DNA are fairly simple in form, but the problem is that by showing them as a literal twisted ladder, we don't have the context for how small DNA really is, because in reality, it's like 20 atoms wide. It's very, very tiny. And this chain of molecules gets stacked millions of times to form a single strand of DNA stretching thousands of kilometers in length, way out into space at this scale. Molecules get progressively more complex as these groupings become larger, such as with proteins, organelles, and viruses. But at a certain point, they become so complex that they become full-on molecule economies, and we call those cells. Let's take a look at blood. The red blood cell is about 7 microns across, making it one of the smallest cells in the human body. It's important because it acts like a FedEx truck, delivering oxygen to the whole body. But even though our scaled DNA would be about a meter wide, a red blood cell would be 5 kilometers wide. They'd appear in the sky like alien dropships coming to exterminate humanity. A single drop of blood contains 5 million red blood cells. In fact, your body produces 2 million of these every second. There are trillions of these running through your veins right now! That is such a crazy fact that I wouldn't be surprised if you took that with a grain of salt. I mean, what if you did? Regular table salt is just a compound of sodium and chlorine, and thanks to the way that these atoms are packed together, they form these really cool looking cubic crystals. Because a typical table salt crystal is about 0.5 millimeter wide, that scales up to over 300 kilometers. This is several times larger than the asteroid that killed off all the dinosaurs. An impact of this size would reduce the entire planet to lava, and this guy would be the destroyer of worlds. So it's obvious that with our atomic scale, even tiny things become massive. But when I was crunching the numbers for this video, I discovered something really weird about pennies. I measured this penny at 19.02 millimeters wide. When you multiply that by our scale of 670 million, you end up with a penny 12,743 kilometers wide. Now, why is that special? Well, the Earth's diameter at its equator is 12,742 kilometers wide. Somehow, the penny at this atomic scale is the same size as our planet, with a difference of only a single kilometer. To put that into perspective, the thickness of the penny would appear 950 kilometers wide. And this really helps put into context just how small atoms really are. Just imagine a giant planet-sized disk filled with tennis balls. But now let's have some fun. Remember when we scaled a proton up to a tennis ball and how big the whole atom got? How big would a penny be at that scale? It would be 1.5 billion kilometers wide. That is the size of Jupiter's orbit around the sun. That is incredibly huge, but can we go even further? Just like an atom, a proton is also mostly empty space. It's actually composed of a bunch of subatomic particles that we call quarks. According to the standard model, quarks are actual literal points with no physical size at all, because size is kind of irrelevant at the quantum level. However, there is some evidence that perhaps a quark is about 2,000 times smaller than a proton. So if we were to scale a quark up to the size of a tennis ball, how big would our penny be then? It would become hundreds of times bigger than our entire solar system, coming in at just under 1/3 of a light year in length. But now we're on the cosmic scale, and suddenly this massive penny becomes tiny again. I mean, our closest neighboring star, Alpha Centauri, is about 4 light years away, and it would take 14 of these pennies just to reach it. In comparison, our Milky Way galaxy is 100,000 light years across. What do we have to do to put a dent into that scale? There is a unit of distance that is considered to be the smallest length mathematically possible before the laws of physics fall apart, and it is called the Planck length.
Now, this is a length of a plank, but this is not what a Planck length is.
It measures out to 1.6 times 10 to the negative 35 meters. And I realize that number might not mean much to you, but this is a number so unimaginably tiny that if we were to apply our tennis ball scale, our penny would be bigger than our entire galaxy. Except to say that is an understatement would be an understatement. The entire observable universe is 93 billion light years wide, and our Planck penny would be 90,000 times bigger than that. Let me show you exactly how big that is. If we were to confine the entire observable universe into just a single pixel on a 4K TV, you would need over 800 TVs just to see our entire penny. That is how small the Planck length is. Infinity goes both ways. Our universe is inconceivably large, and yet it is also inconceivably small. It really feels like a fractal with no end in how big or small it can possibly be. Our only limit is how far we can see. Thanks for watching.